So I need to know what it is in liters. So in setting it up, 750 ml times in a line. Remember that the unit you're given goes on the bottom, milliliters. The unit that I want is in liters. Milli always gets 1,000. So when you take 750, divide it by 1,000, you get 0.75. So I'm going to put that here. So this number is what I'm going to use there. That's the volume, but it's got to be in liters if you're going to use it in concentration times volume. That way liters and liters will cancel. That one. Liters and liters will cancel and leave you with an answer that's in moles. So 2.5 times 0.75. 2.5 times 0.75 is 0.1875 moles. So first step, convert that capital M to what its units mean, which is moles per liter. Then multiply the concentration times the volume. Make sure that your volumes have the same units. If one's liters and one's milliliters, you've got to convert them. They have to have the same units to be able to multiply. So now I know the number of moles, but my final answer needs to be in grams, so I need to convert moles to grams. So 1.875 moles of NaCl is equal to how many grams? Remember, to do that, you're just going to need the gram formula mass. So for NaCl, looking on your periodic table, you find sodium. Sodium weighs 22.99, so I would just round that to 23. The chlorine is 35.45, and we'll just round that to 35. You add those together. There's only one of each. So that's 58 grams is equal to 1 mole. So that's the formula mass. Just add up the mass of each of the atoms in the formula. So in this, 1 mole, 58 grams on top. So that 1.875 times 58 comes out with 108.75 grams of sodium chloride. So sort of 3 steps. 1, anytime you have percent or molarity, put it in its units. If you want to know how much solute, it's always going to be concentration times the volume. That'll tell you how much solute you have. And if you have moles, you've got to convert it to grams using the formula mass. So then the last step is, again, always applying significant figures. 2.5 has how many significant figures? 2. 750 has 2. Right? So my numbers in the problem are always the ones you go back and look at. So see, I want to keep the 1 and the 0 out of 108.75. The next number's an 8, so what is that going to do? What is it going to round to? So 108.75 with 2 significant figures would be what? That would be 3 significant figures. Can you see that? So it's the 8 that has to round up or down. So that would end up being 110. Right? So I'd keep the 1 and the 0. The next number's an 8, which would round that 0 in between, in the tens place, would round it up to a 1. 110, 2 significant figures in that answer. Right? Remember, zeros out front are never significant. Zeros at the end are not significant unless there's a decimal place. I need to keep this. You see that I can't round this to 11. 108 would round up to 110. I have to keep that 0 to show the size of the number. So there'd be 110 grams of sodium chloride in that solution. So just as a note, on Wednesday night, I will give you your take-home exam. So it'll be everything. You'll write all your answers on the take-home exam directly. You'll turn it in the following Monday. Well, not next Monday, because all of next week, everybody knows next week we have no classes. We have no classes on Friday. I don't know if you have class on Friday, but Friday is sort of like Easter, the Easter holiday, because that's Good Friday. And then there's no classes next week at all. That is Easter break. So you have that whole week to work on it. You will turn it in that Monday night. Okay, so that's the 17th. So as long as you can get it to me then, I can get everything graded, get everything put in the computer. And so that way you will have 4 exam grades plus all your mastering stuff and everything else in the computer. And that'll give you a couple of days before the last day to drop, which is the 21st of April. So if you're one that's like sitting on the fence for some reason, not sure if you want to stay in the class, because if you're average, you have until the 21st to drop without penalty. It just shows up as a W. It doesn't, or yeah, it's a W. It doesn't actually hurt your GPA. That's really the big key part for some people, is they don't want it to hurt their grade point average. Okay, to make sure that you pick it up on Wednesday and then you'll give it back to me on Monday. So molarity is one, percent is the other. And so just like the capital M, you got to switch it to moles per liter. When you see the percent sign has no unit. So if you see percent, then you really need to know, is it mass of solute per mass of solution? Is it volume of solute per volume of solution? Or is it grams of solute per volume of solution? And so the words that they use in percent is if they say M to M, that's mass to mass. So if you have a percent M to M, that means that it would be grams of solute divided by 100 grams of the solution. So that would be like adding solvent and solute together. Correct. Like, so starting Friday, so today is the 3rd, 4th, 5th, 6th, 7th. So the 7th on Friday, campus is actually closed Friday because that's considered a holiday. Then 10, 11, 12. So 13, right? 13th. No, it'd be 14th, I guess. Is Monday? I don't know what my dates are. I just can't keep everything straight anymore. Look. Okay, so the 7th campus is closed because of Easter. And then from the 10th through the 14th, there are no classes. So campus is open though. So like if you needed to come and use the computers or the library or anything like that, I will actually be on campus Monday, Tuesday, Wednesday, at least part of each of those days, just because I'm not using my vacation. Okay, but Thursday and Friday I'll be gone, but Monday through Wednesday I'll be on campus. So when you come back, that will be the 17th. That's that Monday, and you'll actually turn in your take-home exam that day. All right. So if you see mass to mass percent, that's grams per 100 grams of solution. If you saw percent volume to volume, so that's like if you mix 2 liquids together. Okay, if you mix 2 liquids together, then the solute is whatever volume of the lower amount divided by the 100 milliliters of solution. So volume to volume would be milliliters of solute per 100 milliliters of solution. So that's a volume to volume percent. The most common one, and like what you usually think of, is you think of you had a solid solute like sugar or salt and you dissolve it in water. So they call that mass to volume. Okay, so this is if you measure out some number of grams of solute and then you dissolve it to make a 100 ml solution. So that's like what we did in lab when you made like 5% salt, 10% salt. You weighed out a solid salt, sodium chloride. You put it in the graduated cylinder and you added water to make that 100 mils of solution. That's what they usually think of as mass to volume. But those are all possible ways of describing the percent. So if you see something that's listed like this, so a 5% solution of sodium chloride, and typically it'll say MV, which is mass to volume. That means 5 grams of sodium chloride per 100 milliliters of solution. So it's not per 100 milliliters of water because the salt's in there too, and the salt does take up some room. So if you need to make a 23% mass to volume glucose solution to feed your newborn snakes, if the final volume of the glucose solution needs to be exactly 200 mils, so I have a 200 with the decimal place, how much glucose will you need? So just like we did before, remember concentration times volume tells you the amount of the solute. It's the same thing here. So concentration times the volume is going to equal amount of solute. But in here, our concentration is percent. So you needed to do with molarity, changing it to moles per liter, you need to take and change that percent to what it means. So the percent in this one is mass to volume. So the percent, 23.0%. If it's mass to volume, that is going to be equal to 23.0 grams of glucose, whatever the solute is, per 100 milliliters of solution. So that's what percent means. That's what that symbol, change it back to its units, because then you can multiply and cancel units out. So you'll just write it out. Concentration, 23.0 grams of glucose, divided by 100 mils of solution, times the volume, and I want 200 milliliters exactly. Do you see that milliliters and milliliters are the same? So my units are in volume are both the same. I don't have to do any converting. I just have these units will cancel. So then you're going to take 23.0 times 200 divided by 100. .0 times 200 and then divide it by 100. And what'd you get? 46. So what about significant figures? In significant figures, how many significant figures in 23.0? When you have a decimal place, zeros at the end are now become significant. So this would be 3. 200 with the decimal place would be 3. So 46, what do I have to add? 0.0. Okay? So to make sure that your answer has as many significant figures as the number in your problems, always go back and check the ones in the problem. Remember, zeros after a decimal place or zeros at the end of a number that has a decimal place, those are always significant. So 200 decimal place means it's exactly 200 mils. So that's 3 significant figures in that number. 23.0, because the decimal place is 0 after, is significant. If I just said 200, it would only be 1. But 200 with the decimal place means it's much more exact than just saying, oh, about 200. That's really saying it's exactly 200. So that's why I would need to add that decimal place 0 at the end. So you want to make a 12% sodium chloride solution to add to your fish tank. You need to add a total volume of 625 mils. So how much sodium chloride will you weigh out? So see if you can figure out this one. Follow the same steps. So I think percent solutions are a whole lot more straightforward because you don't have to mess with the moles and grams per moles and all of that. It's really just making sure your units can cancel. Concentration times volume tells you how much of your solute. So in this one, 12% sodium chloride becomes what? 12 grams per 12 grams of NaCl per, so it'll be over what? 100 mils, okay? So change your percent to what it means. So remember that this percent is going to equal grams per 100 mils or whatever. If it's mass to mass, it'd be grams per 100 grams. If it's mass to volume like this, it'd be grams per 100 mils. If it was volume to volume, it'd be mils per 100 mils. But percent always means per 100. So I'm just changed my percent to what it equals or what it stands for. Multiply it times the volume. Do you see that milliliters and milliliters will cancel when you do that? Concentration times volume tells me that I've got to weigh out 75 grams of sodium chloride. So that tells me how much sodium chloride that I have to add. So I would take the 75 grams of sodium chloride and I would put it in a measuring cup, or if I was in lab, I'd put it in a graduated cylinder. And the question of how much water will you add? Do you know exactly how much water? I put 75 grams of sodium chloride into a measuring cup or into a graduated cylinder, and I would add enough water to make the total volume 625 mils. So do you see that I wouldn't actually add 625 mils? Because the water, it's going to take up some space, but so is the salt. The 75 grams of salt in the bottom of the measuring cup, that is going to, when you start adding water, that's not going to be exactly 625 mils of water. It'll be a little bit less. You really don't know how much. All you know is you want the total volume of solute and solvent to make 625 milliliters. So you could put yourself a little note when you're talking about molarity and percent solution. If you're making up a solution, you don't know exactly how much water you're adding because you're trying to make a total volume. You're making a volume of solute and solvent, so you really don't know exactly how much solvent. You just know the final volume. You know you want to make it 100 mil or 625 mils, whatever the volume it's saying that you need to make. You're just mixing solute and solvent until you make that total volume. Okay, so I gave you out. Yes. So I kind of made on one side of this, so I give you this little half sheet page. And so I try to kind of give you sort of like the steps for these. So in the first one, when looking at concentration, remember that molarity, capital M, this unit means moles per 1 liter, or whatever the number is, moles divided by 1 liter. You always, if you have to find the number of grams, you figure out the number of grams in 1 mole from the formula. So it says determine moles from the formula mass, the grams in 1 mole equals grams per mole. Then molarity times volume is always going to tell you the amount of moles, right? Concentration times volume tells you the amount of solute. If it's a percent solution, I wrote it out what it means if it's moles, or if it's mass to mass, grams per, or if it's volume to volume, or if it's mass to volume, what that's referring to. The other two. So then, did you grab one? Do you need a calculator? Do you need a periodic table? So then the third one. So once we get there, the third one is called parts per million and parts per billion. Parts per million and parts per billion is really a lot like a percent solution, except it's talking about really, really small amounts. Because really, a percent solution is like parts per 100. Because if you have 1%, that's 1 per 100. 20%, 20 per 100. So really, a percent is talking about parts per 100. This is parts per million. So the easiest way to solve for this is this. Always do this. Even though it means you have to do some unit conversions, put your solute in grams, put your solution volume in milliliters. So always put solute, right? So whatever I'm looking at, so make sure that your solute should be grams. Make sure that your total volume, your solution volume, needs to be in milliliters. If you do this, you divide grams divided by mils, and if you want to know parts per million, you just multiply this answer times a million. If you want to know parts per billion, you just multiply this number times a billion. So a million is a 1 with 6 zeros, a billion is a 1 with 9 zeros. So they say like 5 drops of food coloring in a bathtub is about 1 part per million. To give you an idea about how small we're talking about. And 1 drop of food coloring in a swimming pool would be like 1 part per billion. That's how small that is. But in some cases, especially things like some very strong medicine toxins, parts per million and parts per billion can actually come into play. Because a lot of toxins, you might ingest a very small amount, but you ingest it and you don't excrete it. So if you ingest a little, ingest a little, ingest a little, it can actually end up building up and being toxic to the body. So it's not typically like 1 dose. It's what happens if you're exposed to it over time. So even with carbon monoxide, they talk about carbon monoxide in the air. They talk about parts per million carbon monoxide can end up being lethal. And it's because you inhale a few molecules, you inhale more. Over hours, it ends up causing you to lose consciousness and then suffocate. So here's a question. If you see, I have 12 milligrams of whatever in 250 mils, just put, you're going to have to change that milligrams to grams, but you can use milliliters. So just make sure your solute goes to grams. So this 12 milligrams of whatever, I need to put this into grams because that is this, okay? The mass of the solute, I need to find that in grams. The solution, though, is 250 mils, so I'm okay. It's already in milliliters, so check. Okay, I want grams per mil. So I need anything, if the mass is not grams, you got to convert it. If the volume is not milliliters, you got to convert it. So if I take 12 milligrams times in a line, milligrams on the bottom, grams on the top. Milli is 1,000, grams gets the 1. It's just a single unit conversion. So in this one, 12 divided by 1,000 is 0.012. Just do that in your calculator if you're not sure. I just moved my decimal place 3 places to the left. So if I want to know parts per million, I will put 0.012 grams divided by 250 milliliters. And whatever this answer is, I multiply it times a million. That will tell me parts per million. 0.012 divided by 250. And oftentimes you'll find like 0.00000 something. But just make sure then you turn around and multiply this answer times a 1, and then make sure you count as you hit the zeros. I think I just did an extra 1. So 0.012 divided by 250 equals, then times 1, 2, 3, 4, 5, 6 zeros. What did you get? 48. That would be ppm. 48 parts per million. And I will tell you, most of the time, parts per million or parts per billion, you're going to compare it to a acceptable number. So this might be like, the level of this toxin it's toxic if it's over 50 parts per million. So if you got 48, you would say it's not toxic. That's most of the time that you would use parts per million or parts per billion, is comparing it to like a minimum or a maximum amount that you might be able to be exposed to. So now if I'm going to do parts per billion on this next one, same thing. I need my solute to be in grams. I need my solution to be in milliliters. And when I look at this, see that neither of them are. So I have to do a unit conversion on each. So I have to take 0.89 milligrams and I need to put it into grams. And then I can divide it by that 12.5 liters, but I've got to put it in milliliters. I've got to put my units in grams per mils first. So in the first one, 0.89 milligrams divided by 1,000 is going to give me 0.00089 grams. The 12.5 liters, liters on the bottom, milliliters on the top. Milliliters gets 1,000, liters gets the 1. So that ends up being 12,500 milliliters. So I'm going to do this. There's the grams per mil. And then I'm just going to take this answer and multiply it times a billion, which is a 1 with 9 zeros. Having problems with this one, 0.000. What'd you get? Did you get a number? I got 71.2. And that's ppb, parts per billion. So it's pretty straightforward. As long as you put solute in grams, solution in mils, then just multiply times a million or a billion. So here's a couple. So copper in drinking water is toxic above levels of 1.3 parts per million. So if you test a 500 milliliter water sample and you measure 150 micrograms of copper, is this safe to drink? And then the other one is arsenic is toxic above levels of 10 parts per billion. If you detect 0.08 milligrams of arsenic in 7.5 liters of water, is this toxic? So for both of them, you've got to solve for whether there are parts per million or parts per billion, and then just compare them to the maximum level that is given. Okay, so let's look at the first one. So in the first one, remember that you want to put the concentration in grams per mil. So if you look at the copper, it's 150 micrograms. So I've got to go to grams. It's 500 milliliters, so that one, check. It's already in milliliters, so I don't have to do any converting. So I'm only going to convert the mass. So remember, micro means a million. So to go from 150 micrograms to 1 gram, I put micrograms on the bottom, grams on the top. Micro gets a million on the bottom. So when you take 150 and divide it by a million, I got 0.00015 grams. Now I just set them up. So now I have grams and I have mils. So just remember that this is sort of like your rule, whether you're doing grams per mils or, parts per million or parts per billion, you're always going to just put them in grams per mils. So 0.00015 grams divided by 500 milliliters. I just multiply my answer times 1,000,000, which is not that. There should be an extra zero in there. So 1 with 6 zeros. What'd you get? Aaliyah, did you get this one?
I did not.
Rihanna, did you get this one?
No.
Because of the micro thing?
Same with the video.
What'd you get now?
0.4.
So I got 0.3. So now you've got to go back and compare. So it says copper in drinking water is toxic above 1.3 parts per million. So is this safe? Is it less than 1.3 parts per million?
Yes.
Yeah. So it's safe? Yes. So 0.3 is less than 1.3 parts per million. So as long as your parts per million number is less than the limit, then you would say, yeah, it's safe to drink. So here's one. So arsenic is toxic above levels of 10 parts per billion. If you detect 0.08 milligrams of arsenic in a 7.5 liter water sample, is it toxic? So again, I got to put 0.08 milligrams. I'm going to have to convert that to grams. And the 7.5 liters, I'm going to have to convert to milliliters. I've got to have grams per milliliters. So I'm going to have 2 unit conversions first before I can do the math. All of these are just 1 unit conversion because they're either like they're all, there's just 1 prefixed unit. So milligrams goes on the bottom, grams goes on the top, milli is 1,000. So that means that I have 0.00008 grams, 7.5 liters, 1 liter on the bottom, 1,000 milliliters on the top, so 7,500 milliliters. So 7,500 milliliters. So now I have grams divided by mil. Once you get your answer, multiply it times 1 billion. A 1 with 9 zeros after it. 0.12348 divided by 7500 times 1, 2, 3, 4, 5, 6, 7, 8, 9. What'd you get? Yep, 10.66666 repeating. So like,
Would you have put a line on top?
yep, you could have that 6. The big thing though, is it greater than 10? Is 10.6666, yes. So here, significant figures is not such a big deal. Really what you're doing, you don't care if it's 10.00001. It's more than 10, so is it safe? No. That would be considered a toxic chemical because it's above 10. So it is greater than, it never zooms when I want it to anymore. Come on, go away. There. So it's greater than 10 parts per billion. So no, it would not be safe. So your answer is greater than 10 point. It's 10.7 is what I would think of it as. But anything over 10 would be a no. Okay? So that's really the trick. Parts per million, parts per billion. It's not bad. Just make sure that you put it in those units. Because if you try to do it in any other direction, odds are you're going to end up having a mistake and you're going to be 1,000 times bigger or smaller or 1,000,000 times bigger or smaller than the number actually needs to be. Just put it in, put the mass in grams, put the volume in milliliters, multiply it times 1,000,000 or 1,000,000,000, and then just compare it. So then the third thing, or fourth thing, So if you look on that little handout sheet that I gave you, these are really like the 4 math things to think about in this. Molarity, percent solutions, parts per million, parts per billion. The last one's dilutions. So a dilution is just taking something that's more concentrated, adding water to make it less concentrated, right? So their example in here is, they don't use the orange juice analogy that I always used to think of. And that's because people don't use that orange juice anymore. But if you have so you get a water bottle, like a 20-ounce water bottle, they have these little like squirt flavors that you can like just do like 1 squirt, and that like adds this color and flavor to your water so that now suddenly you can drink water. I mean, to me, it always ends up adding weird taste to my water, so I really just prefer water. That's just me. But do you see then, you would agree that the little squirt bottle, that is way more concentrated. Okay, so you wouldn't just squirt that straight in your mouth because that would be really strong. Instead, you put it in the water and that dilutes it. So that's really what we're looking at. I always had the analogy, and Tasha, you probably, do you remember having frozen orange juice concentrate cans? That's how we used to have orange juice. But my father, growing up the way he did, my father, like it always says on the can, like, pour this into a container and add 3 cans of cold water. And so he would always pour at least 4 cans of cold water because there were 4 children plus my parents. And so that like made the orange juice spread out. My entire life, I thought that that's how orange juice tasted. And the very first time we went out and I got orange juice at a restaurant, I was like, what is that? Because I was used to it being really watery and thin. So like regular orange juice was so sweet and thick tasting. I was like, what is that? And they're like, it's orange juice. And I'm like, are you sure? And then I found that out. And I was like, well, no wonder I can't stand real orange. I was like, we got to add some water to this. It tastes better this way. This is my father. He was the one that used to he would buy cereal. And if we ate it too fast, he'd be like, I'm not buying that anymore. Because you kids ate it too fast. Well, what are we supposed to eat? Go out and eat some rocks. I don't know. That was just the family. The whole family routine was always so funny. So in this, the initial concentration is always going to be higher. The final concentration is always going to be lower because we're always adding water, right? So your C1 is always going to be the higher concentration. The C2 is always going to be lower. So which one is going to have a higher volume? The amount of squirt that you add or the amount of the diluted solution? The C, yeah. So V2 is always going to be a larger volume and V1 is always going to be less or lower. So this one's kind of like Boyle's law. So C1 times V1 is equal to C2 times V2. You know 3 out of the 4. You just have to figure out the last one. You'll know 3 of these values, and you just have to figure out what's your unknown, solve for it, plug your numbers in, and use significant figures to round. But you can always expect that your initial concentration is always greater because you're adding water to it, so the final concentration is always lower. Your initial volume is going to be much less and you add water to make the larger volume. So here's like the rule. And remember that you'll know 3 out of 4. I don't like expect you to, I won't give you any where you don't know more than that. You'll always know 3 out of the 4 numbers, and you really just have to solve for the 4th. So here's one. Oh, so the first one actually is a percent solution question. How much magnesium oxide would you need to make a 4% magnesium oxide solution? And I'll tell you that that's a mass to volume. I need to add that. That's a mass to volume concentration. How much magnesium oxide would you need to make a... So remember in this one, concentration times volume tells you how much of the solute that you need. You just have to make sure you change that percent into a unit value. So you take 4.0%. That means 4.0 grams of that magnesium oxide per or divided by 100 mils of the solution. So just change percent into what it means as a unit and multiply it times the volume. Do you see that milliliters and milliliters are the same? So the units are the same, so they will be able to cancel. This is milliliters. It doesn't look like it. It's supposed to be ml. So milliliters and milliliters are the same. So it would end up being 4 times 650 divided by 100, right? Make sure you divide it by 100 at the end. And I ended up getting 26 grams of MgO, magnesium oxide. So what you do is weigh out 26 milligrams of magnesium oxide on a scale, put it into some kind of measuring cup, and add enough water to make the total volume 650 mils. I don't know how much water you're adding, but you're adding enough to make the total solution 650 mils. So again, concentration times volume is what you're typically doing when you have a molarity or percent solution. But if you find a bottle with a 22.5% magnesium oxide solution, then you could dilute this. So I have a more concentrated sample and I want to know how would I dilute it to make this 650 milliliters of that 4% magnesium oxide. So do you see that this is the more concentrated? 22.5 is more concentrated than 4. So this is going to be C1. So the lower one is going to be my C2. What is 650 mils? Is that my starting volume or my final volume? It's going to be the final volume, so that's V2. So if I know C1 times V1 equals C2 times V2, what's my unknown? So V1 is the one I don't know. And you could write it out just like you write out the gas laws to keep them all straight. So C1 times V1 is equal to C2 times V2. How do I get V1 all by itself? So I got to move C1 over to the other side. That's C1, not 2. So I have to divide both sides by C1. See that will cancel. C1 moves over to the other side into the denominator. Then you just can plug them in. So 4.0%, that's C2. 650 mils, that's V2. Divided by C1, which is 22.5%. So see how percent and percent will cancel? You take 4 times 650 and divide it by 22.5. I told you in parts per million, rounding and such doesn't really have a huge factor or play, but in dilutions, you do have to figure out how to round. So 22.5%, how many significant figures? 3. 22.5 has 3 significant figures. Then I have 650 milliliters, so that is 2. And then 4.0 is 2. So that means this 1, 1, the first 2 ones are significant. So what happens to that 5? So that 5, I'm going to end up going from 115. Will I go round down to 110 or round up to 120? You round up to 120. Right? And that way I only have 2 significant figures in my answer. So I would take 120 mils of that 22.5% magnesium oxide. Now when I do a dilution like this, I actually can figure out how much water I have to add. So if 120 mils is the 22.5 solution, and my final volume needs to be 650 milliliters, how much water do I add? How do I figure that out? So in a dilution, you can figure out it because you have two volumes that you know.
So would you just subtract your second volume?
You take your final volume minus the concentrated volume. So 650 mils minus 120 mils would be?
530.
So it'd be 530 mils of water. So I can figure out what the amount of water in a dilution, but if I make up a percent solution or a molar solution, I really don't know exactly how much water. But if I start off with the liquid and I dilute it to a certain concentration, just subtracting the volumes is how you figure out how much water. Okay, so let's do one more and then we'll work on the ones that are on the worksheet, just to give you some practice with them. So what was the original concentration of a glucose solution if you use 275 mils of this to make a 1.75 liter of a 5.25% solution? So you got to figure out, what do I know and what's the unknown? So V1. So remember, volume is always going to be some kind of milliliter, liter. So then 1.75 liters, what is that? V2. So then 5.25% is C2. So I know 275 here, 5.25%. So the one thing to note, you see you have milliliters and liters. So if those units don't match, you got to make them match. Okay? You don't have to worry as long as both are concentrations, both percents, or volumes, both liters or milliliters, and you can use either. You can convert 275 to liters, or you can convert 1.75 to milliliters. It really doesn't matter because they're going to cancel. Just make sure that I've got to make sure that these have the same units. So I'll just take the 275 milliliters and convert it to liters. If I could write my numbers right tonight. 275 ml times in a line. Milliliters on the bottom, liters on the top. Milli is the 1,000. So it's 0.275, because 275 divided by 1,000. So I have to solve for C1. So that means that I've got to move, in this one, I've got to move V1 to the other side. Do that by dividing both sides by V1. Remember, if something's in the denominator, it'll go to the denominator if you move it to the opposite side. So this one, V1, goes from being in the denominator on the left into the denominator or the bottom on the right. So doing the math, 5.25 times 1.75 divided by So in this, I got 33.409099091. So what would I round this to? Right, so if you see 275, 3 significant figures, 1.75, 3 significant figures, 525, 3 significant figures. So the first 3 significant figures is a 33.3. Next number is a 0, so all those round off. So it'd be 33.4% glucose. That's the original concentration, or my C1. Okay, so you just want to make sure that you follow those steps as we go through. So the last part of this chapter is really like more theory stuff. So on Wednesday, we're going to talk about osmosis and diffusion. We're going to talk about like how molecules move from high to low concentration, and then we'll apply that to dialysis. So that's kind of like the last topic in this chapter. So that middle part is the part with all the math that gives the challenge. I guess I have to close. We'll just take the last couple of minutes because we've only got like 12, 13 more minutes. But for the last couple of minutes, we'll just do a couple of these to make sure you've got them. So like I said, this is kind of like the summary of making sure how you follow the steps in this. So that's on the one side, that front side, what molarity is, what percent solutions mean. And then parts per million, and dilutions. So on the back side are some practice ones. So I'll walk you through these ones. What is the molarity of a 2.5 solution of 2.5 liter solutions of sodium bicarbonate, which contains 47 grams of NaHCO3? So remember, I want to know this. So I want to know what is the molarity. So I know that molarity is moles per 1 liter because it's a solution. So it's a some amount of this solute in a volume of liquid. So molarity is moles per liter. So I see liters. So you see the 2.5 liters. So I know what my liter unit is going to be on the bottom. I've got to figure out the moles. I see grams, but I don't see moles listed. So if I know grams, I can go from grams to moles. So in this one, I'm going to have to go from grams to moles. Then I just take the amount of those moles and divide it by however many liters in that volume. And that's my molarity. So to go from grams to moles, what do I have to figure out? How do I figure out how many grams in a mole? Grams to moles. By the molar mass. So I have 47 grams of NaHCO3. I need to know how many grams in 1 mole, so I have to add up the masses. So look at the periodic table. I have NaHCO3. So that means I have 1 sodium, which weighs 23. I have 1 hydrogen, which weighs 1. I have 1 carbon, which weighs 12. Everybody see these? Remember, those are the numbers under the symbol on the periodic table. And then I have 3 oxygens. Each oxygen weighs 16. You got to multiply that times 3. So 16 times 3 is 48. Add those up. Okay? It's the mass of each of the atoms in the formula. Add them all up. So 23, 24, 34, 44. So I got 84. Yeah, 84. So So there's 84 grams in 1 mole. So I'm going to use that like a unit conversion. So if I have 47 grams times in a line, what unit goes on the bottom? Grams. Moles is going to go on top. So the unit I start with always goes on the bottom, moles on the top. So moles gets the 1 and grams gets the 84. $47 divided by 84. And I got 952,381. So I got this number. That number goes on the top in molarity. So that's the number of moles. I'm not going to round this though because it's actually part of my number. I have to take this number and put it here. And I've got to divide it by what? What is the volume of my solution? So 2.5 liters. So whatever the number you get, just divide it by 2.5. So that's 0.55952381. Divide by 2.5. The answer that I end up with is 0.223809524. And that would be capital M. That's molarity. How many significant figures should I keep? Just 2, right? Because if you look at the numbers along the top, 2.5 is 2 significant figures. 47 is 2 significant figures. So I keep the 0 point, because remember the zeros you keep, decimals you keep, but I keep the 2 and the 2. Next number's a 3, so it just rounds off. So they would say it's a 0.22 molar solution of sodium bicarbonate. So if you're given grams and you're given a volume with the formula, you can figure out molarity of a solution. If you're given a percent solution in a volume, you can figure out grams. I told you percent's a little more straightforward. So if I have 500 milliliters of a 12% sodium chloride solution, and again, this would be mass to volume, 12% means what? So this means 12 grams of sodium chloride per 100 milliliters of the solution. So then I multiply it times. Multiply it times the volume. Concentration times volume. You just have to change that percent to what it means. Percent is grams per 100 of whatever. This one's grams per mil. Now don't forget to divide by that 100. So take 12 times 500 and then make sure you divide by 100. Don't forget that 100 in the denominator because sometimes people end up with like a number and it's 100 times too large and that's why. So what would you get? 60. So there's 60 grams of sodium chloride in that solution. So percent, you don't have to worry about moles per liter, moles in grams and things like that. Percent is either just grams per milliliter, grams per 100 mils, or grams per 100 grams. Most of the ones we talk about are solutions where it's a solid dissolved in a liquid. So it's most of the time grams per 100 grams. That's a typical, the most common percent value. So in this one, how many parts per billion is a solution of 0.125 milligrams of lead nitrate in 5.0 liters? Levels over 20 parts per billion are toxic. Is this toxic? So one, I want to find parts per billion. So what do I have to put 0.125 milligrams? What do I have to put that in? Got to put that in grams. So 0.125 milligrams. I need it in grams. What about 5.0 liters? Is that okay? What do I need it as? It needs milliliters. So 5.0 liters, I need to put that in milliliters. Once I get that, divide them, multiply it times 1,000,000,000. Okay? So you take the gram amount, or milligrams, convert it to grams. 0.0125 milligrams is 0.000125 grams after doing the math. 5 liters becomes 5,000 milliliters. I'm dividing those and multiply that answer times 1,000,000,000. And what'd you get? So I got 25 ppb. So you got 25, I got 25, you got 25. Oh, well, it's looking bad for you. Try it again. Okay, 0.000125, divide it by 5,000, then hit equals, multiply it times 1,000,000,000. And make sure you hit 1 and count. I always count 1, 2, 3, 4, 5, 6, 7, 8, 9. Count like 9 zeros as I put them in, because I'm notorious for like leaving a 0 off and then being off by a factor of 10. Okay, so practice those ones. So these last two, these are like dilution questions. So it's really time to go. So I'll quit there. We can do these last 2 ones, and then we will do osmosis, diffusion, talk about isotonic, hypertonic, hypotonic, and then about dialysis. And then I'll finish up chapter 8 on Wednesday. Okay, so we'll do a little more math, just review, and then finish that up for Wednesday.